Hello, I'm Steve. I work for D&B in the UK. My job is kind of technical support and education from the UK office. I'm doing lots of talking, but usually I'm talking for a whole day, so the thought of 5 minutes is quite daunting to me to try and say everything in 5 minutes, so I'll try and do my best. But we're going to talk about the B4, which is one of our newest subs that we just brought out. We believe it's very innovative in the way it's designed, and I've never seen anybody doing what we're trying to achieve here in the way we've done it. So first I thought I'd kind of just start you off with something we talk about quite a lot, which is one of the main issues that we're trying to do when we make things louder with loudspeakers. Generally, you'd have a speaker in a room, and the sound we want to listen to is a sound direct from the loudspeaker. We don't want to listen to all the sound that's bouncing around the walls, because the sound that bounces around the walls arrives later at our ears, and it masks the sound we want to actually hear direct from the loudspeaker. And the sound can keep bouncing around the walls and keep bouncing around, and that's what builds up effectively our reverberant field that we hear when we think about reverb. That's what that is. It's a sound bouncing around the walls and arriving at our ears later and later. So generally, what we do to get around this is we make a loudspeaker that points the sound in a specific direction. So when we think of a loudspeaker, we talk about its directionality. It might be 60 degrees wide by 40 degrees in the vertical or something like that. But we want to try and make a loudspeaker that keeps the energy on our audience and keeps the energy off everywhere else, because we don't want the sound to go everywhere else. A, because we don't want it to hit walls and bounce around. B, if we're outside, we don't want to send sound to the local villages or wherever for them to start complaining about festivals being too loud and things like that. So it makes sense that we just keep the sound on the audience. We don't excite the room, we excite the audience. Now, natural laws of physics, this is an isobar plot. This is what we use to show how directive our loudspeakers are. This is an isobar plot of a standard 15-inch driver. So it's just a speaker that's about this big. And the laws of physics tell us that the higher in frequency we go, the more directive a speaker will become naturally. And there's a rough rule of thumb that if you take any loudspeaker, measure across the front of it, turn that into a wavelength and a frequency, that will tell you the 90-degree point of how wide that speaker is. So in terms of this, a 15-inch driver, 15 inches roughly equates to about 900 hertz. So a 15-inch driver would be 90 degrees wide, or 6 dB down at 90 degrees at 900 hertz. So when we want to think about making a directional loudspeaker down at low frequencies, it means we have to make the speaker bigger and bigger and bigger to do that by normal laws of physics. So if we want to move that lower and move our kind of narrow point lower, the sub range that we're generally thinking about, sub is what, 20 hertz to wherever you decide sub finishes, 100 hertz, 150, somewhere around there. If we think about 100 hertz, the wavelength of 100 hertz is 3.4 meters. So if we want to make a loudspeaker be directive at 100 hertz, without doing any kind of fancy gadgetry, it's got to be 3.5 meters big in order to do that. And that's only 100 hertz. If we think about lower than that, if we want to do 25 hertz, it needs to be 37 meters big to do that. And I don't know many people that want to tour around a loudspeaker that's 37 meters big or put it at the side of a stage or anything. So it basically means we can't make a loudspeaker directional in the typical ways that we would normally make a loudspeaker directional at the higher frequencies. We've got to do something else. So generally the way that we've done it is, if we think about a loudspeaker sending sound out forwards, some of that sound will wrap around the speaker and go behind it. And with a loudspeaker, it's generally pretty much all of it. It may be kind of 3 dB quieter behind, but 3 dB is like the smallest amount you can generally tell a difference between. So the way we've normally made a speaker directional is to cancel out the sound going backwards. We do that by adding a second loudspeaker backwards that is out of phase, or kind of the complete opposite of how the sound is behind the loudspeaker. And then we've got to do various things on there, like a phase change gradually over all the different frequencies to make sure we don't just cancel one frequency, but we cancel the whole range of the frequencies in the sub that the sub might be doing. So that might be 40 hertz up to 100 hertz. The key then is to make it so but by the time the sound from the rear speaker then wraps around and goes to the front, it's actually in phase with what's happening at the front. So we cancel out the sound going backwards, but going to the front, it adds together and it doesn't cancel out going forwards, because that would make it a bit pointless if it did. So to do all of that, we've needed lots of DSP in the amplifiers because we've had to delay the signal to the rear facing driver. We've had to add a frequency change because the sound behind the loudspeaker sounds different to the front of the speaker. So if we're going to cancel it out, it's got to be a different sound. We've had to add all pass filters, phase reverses, lots of various different things that we do with DSP, with digital signal processing. And we've generally done that. Oh, sorry, I'm going ahead of myself. The benefits of doing this means we get punchier defined sub because we hear the sound direct from the loudspeaker more than the sound bouncing around the room and arriving later. So you get more of a chest thump feeling effectively by using this kind of technology. You keep sub energy away from unwanted areas, whatever that might be. That might be away from the wall so it doesn't bounce around and hit us later on. It keeps it away from a stage so we have more gain before feedback because the stage is quieter. It keeps it away from residential areas if we're outside, which might keep a festival running year after year because people don't complain anymore. So there's lots of benefits to this approach. And we've generally, another one, I thought noise exposure for work, that'll tick lots of boxes. If there's people working on stage, it's going to be quieter behind the speakers, so people are going to get less exposure to noise over time. We've generally done that with these loudspeakers. So we've got on the far side, that's a Q-sub CSA stack where we've reversed the middle sub and that's doing the cancellation to the back. That rear-facing speaker has a separate channel of amplifier and all the kind of DSP in there to do that. On the J-sub, which is a bigger version, it has an integral rear-facing 18-inch driver, but again, that's got its own amplifier channel and all the DSP that needs to do that. So the B4, the downsides of this is potentially, these are quite large because we've had to use lots of drivers to make this. We need 2 channels to do this. So we need to use more amplifiers, we need to use more electricity. It's kind of, that's what we've needed to do this generally using DSP. Potentially unneeded SPL levels, because this is quite a lot of speakers for a lot of situations where you don't need a J-sub, which goes pretty loud, or you don't need a stack of 3 Q-subs. A small church, a small theatre, this would be far too big and visually obtrusive to what's going on at that performance. So our new way is using the B4, and here you can see the inside of the B4. And effectively what we've done is we've come up with a way of that rear-facing driver that does a cancellation is actually driven off the same amplifier channel as the front-facing driver now. But all the delay that we need, all the filtering of the loudspeaker to give us a frequency response behind, all the phase changing we need to do, we've done within the cabinet itself. So we've done it by designing the cabinet and the tuning of the volumes inside the cabinet to do all of this. And effectively it looks something like that inside. So we have the front driver doing its normal job, and then the rear driver has a small chamber in front of it and a big chamber behind it. And we tune those to give us a frequency response and the phase response we need, and then there's delay ports coming out from there to the exit. Make those delay ports longer, and it takes longer for the sound to get out, so we can kind of do the delay that we need to do there as well. In terms of the polar plots, we get a response now like that. Instead of being circles that tell us the sound is going everywhere, we've now got a lot of, pretty much all the region where the B4 is working, it's cardioid in its response, so we've got a lot less level going backwards. The other key thing is that in front, the polar patterns sit on top of each other. So wherever you stand in relation to that B4, you get the same sound. You don't get different frequencies doing different kind of patterns, but we call it constant directivity because we believe wherever you sit in relation to a loudspeaker, so you guys are all at different angles to this loudspeaker down here, you're all going to potentially hear a different frequency response. So we want our loudspeakers to give the same frequency response to you wherever you're sat in relation to the loudspeaker. We call it democracy for listeners. Everybody deserves to have the same good sounding gig. So the B4 instead of using DSP, we can get rid of that, and we now use what we call PSP, plywood signal processing. So we don't need all of this extra gadgetry to do this anymore. We've done it within the cabinet itself. A kind of typical example to think about the benefits that it gives us is quite often we put stacks of subs now across the stage, which gives us really good control. Remember I said if you want pattern control down to 25 hertz, you need a speaker 37 meters big. To kind of build upon the technology we've now got, we're effectively doing this to try and make one big loudspeaker out of lots of small loudspeakers. But you can see to do this, we need lots of loudspeakers. So if we were going to do an 8-point subarray with Q subs, we'd need 24 Q subs, and we'd need 8 D12s to do that. So that's a lot of speakers, and it's a lot of amplifiers. It's a lot of foot space at the front of the stage. It's visually obtrusive. It's pulling a lot of electricity potentially to do that. And it may be just completely not needed for the level of the gig that you've got. You might not need the SPL levels that this can produce. Now with the B4, we can do all of that with just 8 B4s and just 2 amplifiers, because we don't need all of this extra DSP now. So we don't need anywhere near as many speakers. We don't need anywhere near as much amplifiers. We're pulling less electricity. It's visually a lot neater in front of a stage. I've just done a theatre spec where using the big cardioid stacks, it would have never gone in a million years because it was too big. If an architect would have walked in the room, he'd have probably hit me if I'd have tried to put those speakers in there. With these speakers now, I can do that and get the benefits of cardioid subs across the stage. And I don't need to put all of this extra amplifier power in there to do that as well, because we have plywood signal processing. So that's a very brief overview on the B4 and why we think it's innovative and why we think it has a lot of different areas where it gives a lot of different benefits, really. Does that make sense? Cool. I guess now it's questions.